Infrared thermography is an analysis method that allows us to detect hot spots and other defects that cannot be seen with a simple visual inspection because there are no visible optical effects. With thermography, we can see temperature differences, and depending on how strong they are, these differences can indicate serious defects or issues that may reduce performance over time. Hot spots with strong local temperature gradients can significantly affect the performance of solar panels and, in extreme cases, may even cause smoldering fires. Infrared imaging is therefore a very useful tool to identify malfunctioning solar panels, module strings, and certain devices within a solar array, as long as external influences such as partial shading or dirt can be ruled out. For reliable results, infrared images should be taken under high solar irradiance, above 600 Watt per m², and under stable ambient conditions, for example with no clouds, low wind speed, and a stable ambient temperature. It is also essential to know the technical details of the solar array, such as module inclination, orientation, string configuration, and variations within the generator, in order to properly evaluate the infrared images. If monitoring data are available, they can support the interpretation, although their accuracy is limited by the inverter. In complex installations, for example on industrial rooftops with different roof layouts, varying string lengths, and different orientations or tilt angles, monitoring data often show large scatter and do not clearly indicate defective components. In contrast, infrared images can clearly reveal modules with high local temperatures, which point to significant power losses and technical risks. In general, large temperature differences indicate high power losses, while smaller differences suggest lower losses. Overall, infrared imaging provides a clear overview of the quality of a solar park under operating conditions, as it allows nearly 100% of the solar modules to be checked for defects that could reduce power output. Alternatively, electroluminescence imaging is highly effective at revealing detailed internal defects in solar modules, but it is not practical for large-scale solar farm inspections due to several constraints. Electroluminescence measurements require the module to be electrically energized, often at night or under controlled low-light conditions, which disrupts normal plant operation and increases inspection time. The method also demands close-range access, specialized power supplies, sensitive cameras, and trained personnel, making it labor-intensive and costly when applied across thousands of modules. Furthermore, environmental factors such as ambient light, temperature, and wind can affect image quality in outdoor conditions. As a result, EL imaging does not scale well for routine inspections and is instead recommended for targeted failure analysis on selected modules, rather than comprehensive field-wide monitoring. Infrared thermography is the recommended primary method for field monitoring. It is a screening and condition monitoring tool, identifying where problems exist and which modules or strings require further investigation. Infrared imaging under normal operating conditions is the most practical and scalable monitoring tool for solar farms.